네, 그러면 시작하겠습니다. Okay, good morning everyone in Seoul, and maybe good afternoon and good evening in people in other area. So welcome to my talk. So today I'll talk about this topic, so understanding hardware mapping model co-design space for efficient deep learning inference. So the goal of my talk is to provide a high-level intuition and insights to general audiences and people working the algorithm side about the interaction between hardware mapping and model for the efficiency in AI semiconductors or deep learning accelerators. And then in the later part, so I'll also introduce one of our latest works from Facebook as an example of the deep learning accelerator. So today, we all know the deep learning applications are pervasive. For example, so we use our face to unlock our phone. This is quite typical now. And as a backbone of that, so we often have the face model, which is a deep learning model. And not only the face recognition, we have a lot of applications such as translation, speech recognition, and image processing. And most of them today are relying on deep learning models as backbone. And from these examples, we can see diverse deep learning models and use cases exist on various devices, not only smartphones, but also, say, smartwatches and virtual reality headsets, and so on. So, but what are the challenges of running those deep learning applications on those devices? So mainly, we have two challenges, so energy and latency. Why are they important? So for energy, it is directly related to the battery life and also thermal dissipation. And also latency, we don't want the device to run very slowly. So this is directly related to the user experience. The similar challenges exist to the data center or cloud devices as well. But in this talk, I'll focus on the edge device cases. So what are the characteristics of deep learning inference workloads? First of all, they involve heavy computation, typically billions of computations. That means we need many number of cores for parallel computing to support this kind of computations quickly. And it also involves heavy data movement because there exists millions of parameters typically. That means we need to maximize local data reuse to fetch data so many times from the DRAM to chip, which is very expensive, typically in 100x scale compared to the computation energy on the deep learning accelerator. So for the first reason, the CPUs are not ideal for the deep learning inference. For the second reason, GPUs are not ideal for deep learning inferences of workloads. So because of that, people are developing specialized hardware chip, or typically in Korea, I heard it is often called AI semiconductor. So which is, I will refer to that as DL Exclamators in this talk. So this is one example photo of the DL Exclamator, which is Iris. The typical structure of these kind of accelerators are something like this. So it has an array of PE, which is processing element, and they are small compute units with for example, one multiplier and one adder, and small memory, which is marked as pad here, which is scratch pad. Scratch pad is a custom memory attached to the PE. And often the DL accelerators have on-chip global buffer, which is the central memory to temporarily store data in the central place. So what are the features of DL accelerators? First of all, they provide high parallelism via thousands of PEs or processing elements. And they also optimize data communication via custom network on chips, which is the interconnect across the PEs and the global buffer. And they maximize the on-chip data reuse via data flow. The data flow means how we compute the deep learning workload on this hardware. So I'll go into the details in the later part of this talk. So first two features gives us a significant latency benefits, and the last two features give us the energy benefits. So by these features, DL accelerators are becoming more efficient for the DL inference workloads. So far so good. So we knew that latency energy-wise it is good, but what exactly determines the deep learning accelerator's efficiency? So to understand that, let me bring a example of the buffet restaurant. So let's say the customers wanted to get the steak and sushi from the buffet restaurant, and we want to serve that. And let's think about two examples of buffet restaurants. So one is the Top Chef's buffet restaurant, and the other is the specialty chef's buffet. So in the Top Chef buffet restaurant, so we have one Top Chef with a lot of salaries, as we can see here. But the Top Chef can cook, for example, 2x faster than specialty chefs for each menu. But the Top Chef wants to clean the kitchen before changing the menu as a professionalism. In contrast, specialty chefs buffet, so each chef can only handle one cuisine. For example, we have sushi chef and steak chef in this example, but they cost less salary than compared to the Top Chef. And this is the example timeline of the cooking. So the sushi chef takes the sushi and steak chef takes the steak, but Top Chef can handle all of them very quickly, as we can see in this example. So to understand the impact of the menu, so let's change the chef menu assignment here. So as you can see in the right side, so compared to the previous one, so I switched the assignment between sushi and steak. So now sushi chef cooks steak and steak chef cooks sushi. And as you can see, so sushi chef is not familiar with steak, so she takes more time. Steak chef is also not familiar with sushi, so takes more time. So as you can see, chef menu assignment affects the efficiency of the buffet restaurant. And what if we change the order of the cooking for the Top Chef buffet? So let's revert the specialty chef's buffet's timeline and let's change the order of cooking in the Top Chef's buffet. So in this example, the Top Chef cooks steak first, then sushi, steak and sushi, and it involves a lot of cleaning in the middle. So apparently it is more inefficient than the original timeline. What if we change the menu? So the customer suddenly wanted to get a steak and noodle. The Top Chefs can still provide the noodle in a very fast manner, but unfortunately, both of the sushi and steak chef are not familiar with noodle. So if we assign to sushi chef like this, then it will take so much time like this. So what determines the buffet restaurant's efficiency? By efficiency, I mean the cost of the buffet restaurant and serving time. So we've seen that menu affects the serving time a lot. And also we found that the cooking order and the portion and the menu assignment also affects a lot on the serving time. And finally, how we organize our restaurants, so either Top Chefs or specialty chefs, that comes with different costs. So we can understand the vectors that affect the deep learning accelerator efficiency in a similar manner. So in deep learning accelerator, the efficiency is translated into energy and latency. So the buffet restaurant cost is similar to the energy, is translated into energy here, and the serving time is translated into latency. And the menu for the buffet restaurant is the deep learning model as workloads to support. And how we cook the menu, so cooking order and portion and assignment, that is all about the compiler mapping. So compiler mapping means how we compute those incoming DL model inference workload on hardware. So this is exactly related, similar to the cooking order and so on. And then lastly, so the hardware architecture. So it corresponds to the buffet restaurant style, either Top Chef or multi-specialty chef, and how many specialty chef we want to hire, how good the Top Chef it is, and so on. So these are three factors that affects the DL accelerator's efficiency. So far I provide a brief introduction of the factors that affects the deep learning accelerator's efficiency. So next I'll go into the impact of the model and mapping on efficiency. And next I'll discuss the impact of hardware architecture on efficiency. And as a part of it, I will introduce one of our latest works, Herald, as an example of the hardware architecture. And I'll summarize and conclude my talk. So let me begin with the impact of model and mapping efficiency by discussing the recent deep learning workloads. So these are interesting examples of deep learning workloads nowadays, which is real-time and multimodal. So for example, for autonomous driving, so there are many subtasks such as the vision-based navigation, lane detection, and so on. And virtual reality side, it also has a lot of subtasks such as eye tracking, image segmentation, and so on. So what are the features of this kind of latest DL workload? It consists of many periodic tasks with different processing rate. And it is based on heterogeneous deep learning models to support this kind of heterogeneous subtasks. So let's take a look at those subtasks more in detail. So for vision-based navigation, for example, so this is just an example, it's not exact model, but let's say we are using this kind of model. So I'll not go into all the details of this one, but please take the color as the different layer operations. And for lane detection, because it does different tasks, so it will require a different model. And one example could be something like this. So as we can see, we have a lot of diverse layer operations in these kind of workloads. And if we take a look at the virtuality side, for example, so for image segmentation, so this is an example from UNet. So one characteristic of the segmentation workload is we first begin with the high resolution and we reduce the resolution and increase the number of channels or depth here. And we restore the original resolution to perform the segmentation on it. But in contrast, for example, eye tracking, for example, so this is a typical structure of actually CNNs. So we start from the high resolution feature, and as we get to the last layer, so we reduce the resolution and increase the channel, and we don't restore the original resolution. So here, what we can observe is the layer size is also diverse. So size, or sometimes we refer to it as shapes. So we have diverse layer sizes, and those two are sources of the heterogeneity in the workloads. So these are example models and example layers inside those models. So I will not go into all the details, but the point from here is it has many different layer operations and many different layer shapes and sizes. So to make it more intuitive, let me bring the example, the buffet restaurant example again. So let's say come to the steak and noodle is another operation and so on. So ResNet 50 is something like large steak, medium steak, and small steak. And MobileNet 50 is something like medium steak and sushi is sushi. And UNet is large steak, medium steak, and noodle. So we can expect this kind of heterogeneity in the workloads. So the main takeaway from this is that recent DL workloads are heterogeneous in layer operation and sizes, and they are the sources of the heterogeneity in these workloads. So far I discussed the recent DNN workloads. So considering that, let me discuss the impact of model and mapping. So this is I'm revisiting this slide. So across the three elements, I will first talk about the DL model and its impact on the energy and latency. To understand that, let me bring a relatively simple example. So I will not use the exact DNN operator, but for simplicity, I will use the matrix vector multiplication example. So what it does is, as you know, for this figure, I transpose the vector B to make it look like the inner product for an intuitive example. So what it computes is the element-wise multiplication across all of those three pairs in the matrix A and vector B in the shaded area. And we accumulate all of the multiplication result to get the one output in the resulting vector here. And we do the same thing for the C1, changing the row here, and then we repeat until we compute all the elements in vector C. So let's say we want to run this workload on this example accelerator that has 3 PEs, which are compute units, and it is also attached with the global scratch pad, which is global memory. But in this example, for simplicity, I'll assume infinite memory size and infinite bandwidth for simplicity. So let's map this operation onto this accelerator. And to do that, let's parallelize these computations, multiplications. Again, for simplicity, I will not discuss the reduction side, so I will only focus on the multiplication side. So if we map these three computations onto these three PEs, then we can map each pair of the multiplication like this. A00, which is the leftmost one, is multiplied by B0, which is the leftmost one in the vector B. They are, it is assigned to the P0 in the same way to the P1 and P2 for rest of the elements here. So here we can observe that, okay, we are utilizing all the P's inside this accelerator, which is good. We are utilizing 100% of the PEs. But what if the layer changes, so the model changes? So in the next example, so the model changes the dimension like this. So instead of the 6 by 3, so it became 6 by 2. Then let's do the same thing. So we will map this onto PEs, we parallelize this dimension. But in this case, we don't have enough items to compute for three PEs because we have only 2 in this dimension. That means the utilization drops to 66% in this case. So here's the main takeaway. So model hardware dimension mismatch is one of the significant sources of inefficiencies in DL accelerators. So in addition to this one, so there are many considerations such as layer operator support and so on, but this is the one intuition I want to share in this talk. And let me discuss the impact of the mapping and hardware architecture to energy and latency next. So this is the same example as the previous one, but the question is, can you improve the utilization here without changing the hardware? The answer is, of course, yes, by changing the mapping strategy like this. Instead of parallelizing the row, we can parallelize the computation across rows instead of columns. By doing that, we have 6 computation to perform on this accelerator. That means we can map 3 items for the first time slot and the next 3 items in the following time slot. And by doing this, we achieve the utilization of 100%. So from this example, we can see changing how an operator is computed impacts the efficiency of inference, as we can see here. Let's also take a look at the impact of hardware. So suddenly we got very large accelerator like this. So we got 6 PEs here. That means we can map all the 6 computation at the same time and still achieve the average utilization of 100%. However, by doing this, the PEs will take a double area. So that's the cost for doing this. So just increasing the number of PEs is not always the ideal solution. And also, there are many other factors we need to consider. So say if the memory bandwidth from the global scratchpad is, say, 32 bytes per cycle, but each PE requires 32 bytes per cycle, then the global scratchpad can fit only 1 PE at 1 cycle. That means even if we have infinite number of PEs, we can only realize 1 PE at the same time. So there are many other considerations like this bandwidth balance problem. So the takeaway is that the large hardware is not always the best solution because we have those kind of effects also an area and power budget as well. But the changing the hardware also affect the efficiency. So one thing I wanted to highlight is that the mapping space, so how we compute the DL workload is huge. The number of ways to compute the DL workload is huge. So because many DNN operators are high dimensional, and also it has large sizes. And the more dimensions and the more optimization opportunities via mapping. So for example, of one of the ResNet 50 layers, so it has more than billions of the available mapping strategies exist only for one layer. So the mapping space is huge. So this is a more concrete example of the high dimensional operator, so which is Com2D. So I will not go into all the details of this one, but basically I want to show that how many dimensions it has. As you can see, it has 7-dimensional computation if we include the batch. And the data is also high dimensional, which are 4D tensors. So this is a high dimensional computation and high dimensional data, but how do we fit that onto the hardware, which is actually 2D mostly? So that is the mapping problem and data flow problem. So we have, say, for 2D example, we have 7-dimensional network layer like this. And computation space is the cross product of all of the dimensions like this. And we are trying to map this computation, high dimensional computation onto 2D array. So because of that, we naturally need to slice the computation into smaller chunks and map them onto the 2D array in one by one. So that's why we get data flow. So by having multiple chunks of the computation or tiles, we need to determine what is the order of the computation across those tiles or the computation slices. And also we need to parallelize the computation, but there can be a lot of different parallelization strategies, such as we can map the depth across over the PEs, or we can map the width of the activation across the PEs. So there are many different variants of that. So the combination of the computation order and parallelization strategy, so they are together termed as data flow. And we also need to, the data flow is basically a strategy how we want to map those operators onto QDP array. But we also need to determine actual size of the mapping. So which means it's a concrete instance of data flows. So if we parallelize to the depth or channels, then how many channels do you want to map at the same time? So that's the exact tile sizes, and that makes the data flow to be mapping. And the implication of those are the amount of data we use in hardware and compute unit utilization, and both of them are related to the critical metrics such as energy and latency. So far, we've taken a look at the impact of model mapping on efficiency, and we got a sense of what's the data flow and mapping. So let's take a look at some data, some realistic data to understand the trade-off space. So first, let me briefly introduce this one. So this is the one slide I visited in the previous slide. But the question is, how do we quantize the impact of the model mapping and hardware on the efficiency, which are energy and latency? So for that, there are many kind of cost and benefit models, such as the time loop and the interstellar. But in this talk, I'll discuss Maestro. The Maestro takes these 3 vectors as inputs, and it has a lot of internal analysis engines like this. So tensor size analysis, clustering, and reuse, and performance costs like that. And it reports the overall latency and overall energy and what's the hardware requirement and so on. So the example output is something like this. So for each layer for the ResNet 50, so we get runtime in cycles and energy and so on. So it is quite fast, 0.49 seconds for ResNet 50 on NVIDIA Dl Exclamators, and it's validated against RTL simulation. So I will not go into all the details of this cost model, which is because it is not the goal of this talk. If you are interested, please take a look at the paper or website. But the reason why I introduced this one, this Maestro, is that because I will use Maestro generate results for the case study in the next slide. So let's take a look at the setting of the case study. So I'm using Maestro for that, as I mentioned. And for hardware config, so I'll fix that as to have the 256 PEs or the compute units. And I'll fix the memory bandwidth from the global memory to the PE. And I'll change the deep learning models first. So I'll have these 4 classification models, and I'll have this one segmentation model. And I'll also change the mapping to understand the interaction of the DL models and mapping. So I'll use 5 distinct mappings. So they are labeled as CPXP or something like this. But they basically mean that P means parallelized, and the integer before P represents the dimension ID, which is listed in the table here. So basically, these five mappings parallelize different dimensions. And this is the data I'd like to discuss. So it can be seen quite much, but let me walk through one by one. So the upper row shows the runtime or latency results, and the lower row present the energy results. And each column represent the result for each model, so ResNet 50, BGG, and so on. And the last column has the average number. And x-axis of each plot has the mapping style, and y-axis, it has runtime energy, as I mentioned. And one thing I wanted to mention is, so it has breakdowns in the colors here. So I have legend over here. So basically, they mean a different combination of the layer sizes and layer operation. Or you can treat them as a different menus from the buffet. For example, the red one is the steak and blue one is sushi and so on. So you can view in that way. And the different mapping styles are different specialty chefs. So in this case study, so we are taking a look into the buffet restaurant, which hires only one specialty chef. And we are taking a look into different cases of the different specialty chefs. So I will not go into all the details of the old result here, but I'll highlight some of the interesting results here. So for the latency or runtime here on ResNet 50, so we can see the last mapping style KCP is better than YXP mapping style. However, if we get to the UNet, then we can observe that actually YXP style, for example, the sushi chef is better than steak chef overall, for example. But in this model, the result was actually opposite. So the takeaway from this one is that no single mapping is ideal for all the models and layers. And we can also take a look at this average case. So unlike other plots, I have adaptive here. So by adaptive, which means if we change the mapping style, which fits best for each layer, then what's the result? So to use the buffet restaurant example, if we change the specialty chef for each menu, then what will be the efficiency we can expect? So in this evaluation, so we've seen that we can reduce the latency by 37%, and we can reduce the energy by 10% compared to the best options in each average plot. So the adaptive or flexible mapping, so we term this one as a flexible mapping. So we choose the best mapping style among evaluated mappings for each layer. So this can definitely improve the efficiency. So EDP gain, so energy delay product gain from this approach was actually on average 43%. So how can you exploit this? So that's the next topic. So let me discuss hardware architectures for exploiting this opportunity. So let's get back to the buffet restaurant example again. So this is exactly the same example. So we had Top Chef's buffet and specialty chef buffet. And by buffet restaurant means we want to support heterogeneous menu. That means that is closely related to the approaches I want to explain for deep learning accelerators, which are reconfigurable data flow accelerator and heterogeneous data flow accelerator. For reconfigurable data flow accelerator, or RDA, is similar to the Top Chef approach. So it can adapt to new workloads and compute them very efficiently, but it requires some cleaning time or for the chef, which is the reconfiguration time to change the internal kind of signals to adapt to the new workload. And for heterogeneous data flow accelerator, it is similar to the specialty chef buffet restaurant. So like sushi chef and steak chef, so we have separate small components within an AI chip. So the red one takes the red workload and green one takes green workload. So those approaches, so let me revisit those. So the first approach was the reconfigure data flow accelerator, RDA, which is Top Chef restaurant. So examples are Mary and FlexFlow and so on. So they changed the internal signals to adapt to the new workload like this. So the yellow ones is the active PE and the black one is inactive PE. And as you can see by reconfiguration, we can change the active PEs and inactive PEs. And this can provide better efficiency for a specific workload. And you can reconfigure again and again for new workloads and so on. But the specialty chef approach is the heterogeneous data flow accelerator, or HDA, which is the work I'll introduce today, which is Herald. This is a new class of deep learning accelerators. So let's take a look at more details of this approach. So what are the heterogeneous data flow accelerator again? The approach is basically, yes, deploying multiple specialty chefs or multiple fixed data flow accelerators that can support only one type of workload very efficiently, but not that efficiently for other workloads. What are the benefits of this approach? First of all, flexibility. So we can assign the best menu for each chef. That means we can cherry pick the most preferred sub-accelerator or the specialty chef for each menu or each layer. And specialty, as we've seen in the example, so specialty chef usually requires a lower salary than the top chef who can manage all the menus across all the menus in the world. So it costs lower, it requires lower costs mainly because it requires simpler hardware than the configurable data flow accelerator, because it doesn't require complicated hardware structures for changing the internal way of the processing. And we can also exploit the model parallelism. This is related to the characteristics of the recent DL workload. So we've seen that, okay, we have heterogeneous and multi-DL model workload. We can simply parallelize those models across these sub-accelerators, which is similar to the specialty chefs can cook menus at the same time in parallel, while the top chef can only cook one thing at the same time. And this is, certainly preferable for multi-DNN workloads. But certainly it also comes with some challenges. The first one is we need to distribute the finite hardware resources across sub-accelerators. That means each specialty chef can be slower than the top chef if we compare one by one. And we need to distribute the valuable hardware resources such as area and power budget to sub-accelerators. That's one challenge. And each sub-accelerator will share the global resources such as the global buffer or the off-chip bandwidth, so which means the width of the way from the DRAM to the chip. This can delay layer execution sometimes. If the global resources is completely occupied by a certain sub-accelerator, then other sub-accelerators need to wait until the resources are available. And we need to anyway run layers in dependency order. So that means we have certain order of the computation within each model. And it can sometimes delay the layer execution because the layer one is computed by one sub-accelerator, but it is not finished yet. But second sub-accelerator is available, but for the layer the next layer, but because the previous layer is not finished yet, the second sub-accelerator need to wait. So something like this. You can think of the course in a restaurant. So the course need to go out in a certain order, the appetizer and the entree and dessert. So that can delay some of the chefs to cook dessert before the entree is finished. So the first challenge gives us the first optimization problem, which is hardware resource distribution. And the last two, the challenges gives us the second optimization problem, which is the layer execution schedule. We need to wisely schedule the computation on HDAs. But what are the impact of each optimization problem? So for hardware resource distribution, we observed the 17% of EDP or energy delay product, which considers both of the energy and latency. And for the second optimization problem, we observed this 24% of impact. So the takeaway from this one is that the heterogeneous data flow accelerators, or HDAs, need to be carefully optimized. That's why we developed a heterogeneous data flow accelerator optimization framework called Herald. So let me give a quick overview of the Herald. So the inputs to the Herald are the workload descriptions, which means the deep learning models, and the total hardware resources we have in the heterogeneous data flow accelerator, and data flows to use for each sub-accelerator. So that means we need to specify the menus we want to cook at the buffet restaurant, and we want to specify the size of the buffet restaurant and number of chefs. And we also want to determine the specialty of each chef. So if we want to have Korean chef, the Chinese chef, or Western chef, and so on, or we could have American chef and the Italian chef instead, so something like that. So using those inputs, Herald generate the optimized HDA design parameters, such as the partitioning across the sub-accelerators. And it also optimized the schedule, the execution schedule, considering all the dependencies and the global resource occupancy and so on. And it gives us the expected overall latency and energy. And what do we have inside? So the Herald has the hardware design space explorer for optimizing the design parameters, and layer scheduler, and they are iterated inside to optimize both of them. And as a backbone, so we have extended Maestro, which is the cost model I used for the case study in one of the previous slides. So what is the use case of the Herald? So I wanted to highlight that the Herald is doing the software and hardware co-design. So this is the example stack of the deep learning accelerator design. So we have model and mapping or data flow and schedule, and the accelerator architecture or hardware architecture. And in the more lower level, we could have circuit or devices aspects. The use case of the Herald focuses on these two co-design. So layer execution schedule and accelerator architecture, we co-optimize that. We can use it in design time. So this is a full capability. And instead, we can also use the scheduler only. Once the HDA is deployed and the workload changes, then we can also use the scheduler to optimize the schedule again to adapt to the new workload. So this is compile time or runtime. So the Herald can be used in the accelerator design time or compile time or runtime. So I'll quickly go over what we are doing for the optimization. So for hardware resource distributions, we distribute we determine the P partitioning. So how many Ps we want to give for each sub-accelerator. And also we determine the bandwidth distribution from the globe buffer, so memory bandwidth. And we basically shift the design space, but we also use some sophisticated ways such as random binary sampling and so on. And this is quite standard approach for the hardware resource, this kind of optimization problem. And let me quickly go over the scheduling, what Herald does. So this is an example model. So each circle represents each layer in each model, and the number represents the order of the layer in each model. And we need to consider layer dependency and global memory occupancy. So we first do the layer assignment considering the preference of each layer to each sub-accelerator. So if this is steak, we want to assign it to steak chef. If it's sushi, then we want to assign to the sushi chef. But here we also consider not only the layer preference, but also global load balancing. So that's why we see red circles in the both sub-accelerators here. And we determine the order of the execution, considering the layer dependency, and we construct a schedule. So we consider the memory constraint and layer dependency together here. And we do some post-processing for fixing some inefficiencies. So this, to sum up this approach, so we exploit the model parallelism and layer preference of sub-accelerators, which means the menu and chef assignment. And only the heterogeneous data flow accelerator exploits both of them. So let me quickly go over some case studies using Herald to understand the impact of hardware architecture in the HDA. So we varied the accelerator size targeting different use cases from edge mobile cloud. And we evaluate across 3 workloads targeting AR/VR. So we have 2 workloads targeting AR/VR use cases and 1 standard workload, which is MFPerf. So we compared the fixed data flow accelerator, the 1 specialty chef buffet, and scaled up FDA, which means a buffet that hires multiple of the same specialty chef, so such as Korean chef to support the buffet restaurant, something like this. And the third one is the reconfigurable data flow accelerator, the top chef buffet. And the last one is the specialty chef buffet, which is HDA, or heterogeneous data flow accelerator. So this is the overall result. So it looks quite complicated. So let me walk through it one by one. But these data is to answer the question, how do HDAs perform compared to the others? So let's focus on this result for simplicity. So on the x-axis we have energy, and on the y-axis we have latency, and the HDA has different colors, as you can see here, and RDA, which is the top chef buffet, is marked as a cross here, and FDA, 1 specialty chef is star, and SFDA is multiple, the same specialty chef is marked as in this symbol. So one thing I'd like to highlight is that the top chef buffet, or RDA, the reconfigurable one, achieved the best latency across all the design points, but it required a lot of energy. And we can also observe there are a lot of suboptimal HDA design points, but we can also see many HDA design points are on the Pareto curve, as we can see here. And FDA and SFDA, they are not Pareto optimal, so they are not desirable. So let me summarize the overall results. So compared to the FDA, the 1 specialty chef buffet, our approach to the HDA provided 5% lower energy and 65% lower latency. And compared to the RDA, which is top chef buffet, it provided 22% lower energy, but at the cost of about 21% higher latency. And FDA and SFDA are not on the Pareto curve. So what is the main takeaway from this result? So I'd like to highlight that the RDA is also a good approach. So not only the HDA, so they are all both Pareto optimal, but HDA is more beneficial for low energy, and RDA is more beneficial for low latency. And this data answers to the question, how does optimized HDA look like? So this is an example. So what if we have 2 specialty chefs? So one is the NVIDIA style chef. Well, we can see it as a kind of steak chef, and sushi chef here, which is Shidena style of accelerator here. And each row represent different workloads and different use cases, edge, mobile, cloud. And I will not go into all the details about this, but oh yeah, and also this number represents the number of PEs, optimal number of PEs to assign to each sub-accelerator. So here, what you can observe is this is not 50 to 50. So this is not half and half. That means the optimal hardware design is not trivial. It's just not 50 and 50. It needs to be carefully optimized. And this data answers the question, what if workload changes after deployment? So it has also latency results on the left side and energy results on the right side. On x-axis, we have different workloads, and we have different bars in each workload, which represent different accelerator styles from one specialty chef buffet, FDA, and until the HDA. And HDA has different variations here. So HDA means HDA optimized for AR/VR-A workload. HDA-B means HDA optimized for AR/VR-B workload in design time, I mean. And HDA-M means one optimized for ML/Perf. And what we can observe here is if we run AR/VR-B workload on different variants of the HDA heterogeneous data flow accelerator, we see certainly HDA-B initially optimized for the AR/VR-B works the best, but HDA-A also works almost similar to the HDA-B, and we can observe HDA-M is actually worst across all of them. It's not surprising because it is optimized for different workload at the beginning. We can observe the similar trend here, but still they have slight differences in latency, but energy-wise they are almost similar. So the summary of the result is something like this. So impact of workload change for HDAs is 4% latency and 0.1 energy increase. That means it is not a significant amount, so optimized HDAs are quite robust to workload changes using the scheduler. So yes, what we did is we just scheduled the workload again for the new workload for the existing HDA. So we have more results available in the paper, so please see our paper in HPCA 2021. So let me summarize my talk and conclude. So I will go over main takeaways. So we've seen that no single data flow or mapping style is ideal for all the models and layers, which motivated the flexible mapping approach. And flexible data flow accelerator can adapt their mapping or data flow to different models. And two example hardware to support flexible data flow was the RDA and HDA, which is the Top Chef restaurant and specialty chef restaurant. And optimized heterogeneous data flow accelerator and our reconfigurable data flow accelerator are both part optimal with different strengths in latency and energy. And the hardware distribution of the optimized HDA was not trivial. It was not 50-50, if you remember the results. And optimized HDAs are robust to workload changes using the Herald, the scheduler, to adapt to the new workload, thanks to the Herald, which is the co-optimization framework. So let me conclude my talk in this way. So we have many new workloads such as AR/VR, and they are heterogeneous and multi-DL model workload. And they construct a complicated co-design space across the deep learning model, mapping and hardware architecture, and they determine the efficiency of the accelerator, such as energy and latency. So we need to explore this space carefully to maximize the efficiency, the energy and latency. So at Facebook, we already labs in our team, so experts from each domain works together to enable this kind of co-design. And we believe this is the right direction to achieve the optimal efficiency on devices to support deep learning workloads. So this is the end of my talk. So thank you for your attention, and please feel free to ask any question if you have.